Ring, ring. Vince, how are you? This is George Merlis from the Pittsburgh Post-Gazette.
Good morning, George. How are you today?
I'm fine. I had some questions about you, about this thing you're working on here. You're a NASA employee working with the Department of Energy, and those are the guys who build nuclear weapons. Is NASA getting into the military business?
Well, no, NASA is not, but we are partnering closely with the Department of Energy to develop new, very highly efficient power systems for powering our missions to the deepest regions of the solar system and beyond.
Now, you've been using nuclear power in space for a very long time. In fact, Voyager, which may or may not be at the very edge of our solar system, or may even have passed it and be in interstellar space that's powered by that. If it all works, why do you need new sources?
Well, you're correct, George. We have, in fact, a rich history of using nuclear-powered sources for generating electrical power on our spacecraft that go back to the dawn of the space age. However, we are always interested in trying to develop more efficient sources of power for our spacecraft that can either generate the same amount of power using less fuel or that much more power using the equivalent amount of nuclear fuel.
Now, the nuclear fuel in question is plutonium, and I know from 60 Minutes that this is the deadliest substance known to man. Couldn't you use a safer radioisotope?
Well, in point of fact, George, the plutonium-238 that we use is actually very safe. It is not weapons-grade plutonium. It is actually just a heat source. That's the bottom line. And it's safe because of how we process it. We actually encapsulate the plutonium-238 into a ceramic material that is so safe that were it to fall onto the floor, it would just be like dropping a coffee cup onto the floor.
Yet you're going to put this, and you have put it in the past, on top of a solid-fueled rocket which has the potential to blow up. Are you not, in effect, creating the equivalent of a nuclear bomb?
Well, no, George, in point of fact, we are not. As you may know, rocket launches are very safe with less than a 1% chance of failure, again, dating back over 50 years of the space program. And even if there were to be a launch failure, we are designing this system to be contained inside of multiple layers of containment within the spacecraft and within the power system, such that release of this material is very highly unlikely. And as I said before, even if some were to be released, it would be easily collectible on the ground because of the ceramic form that the material takes.
Why do you need nuclear material in the first place? Isn't solar power sufficient?
George, solar power is used for many spacecraft, but the intensity of solar radiation is only really usable about to the orbit of the planet Jupiter. So beyond that point in the solar system, the intensity of the solar radiation is too faint to generate electricity that's usable on the spacecraft. So these systems provide electricity through generating heat that is very long-lived, and in fact will be able to generate power actually beyond the usable life of these spacecraft as they travel well beyond the orbit of Jupiter.
Is there any risk to the planets that you're visiting from this radioisotope material?
George, that's a good question. We have a very rigorous planetary protection protocol that the United States has signed on to. It's actually an international treaty, and we take that very seriously in developing the requirements for our spacecraft design. And in fact, the Curiosity rover that is currently operating on the surface of Mars has a radioisotope power system on it, and we took over 40,000 individual samples or swabs of that spacecraft before we launched it to make sure that the spacecraft was safe and it was not carrying any contamination to the surface of Mars from the Earth.
You're working with the Department of Energy. NASA is known for its outreach and public engagement. DOE, which is appropriate for the agency that builds and maintains our nuclear weapons, is a lot more closed when it comes to public engagement. Are you sensing a culture clash? Are you suffering from culture clash there?
George, that's another good question. Every organization in the federal government has its own unique culture and traditions and norms. And so anytime two agencies like this work together on a mission of mutual interest and benefit for the nation, you're always going to want to make sure you're paying close attention to melding those cultures to get the best out of each agency, what each agency can bring to the mission. And so this is something that we do spend time talking about and paying attention to make sure that we're taking advantage of the very best strengths that both NASA and the Department of Energy bring to a mission like this.
Anything else you think my readers here in Pittsburgh should know about this project that you're working on?
Yes, I'd like to leave behind an image of this advanced radioactive isotope power system in their mind. It is like a deep space battery that never has to be recharged. It will just keep going and going throughout the course of the mission as we travel deeper and deeper to the farthest reaches of the solar system.
Okay, thank you. May I have a mic check, please?
Yes, we are developing a new deep space battery that never has to be recharged.
Vince, before we went on the air, you said that NASA is developing a new deep space battery that never has to be recharged. How can you have a battery that never needs recharging?
You can have a battery or a system that functions just like a battery by putting a very long-lived source of heat into it and then using a technology to turn that heat into electricity.
And what are we talking about? What's the source and what's the electricity and what's the system?
So what we're talking about is a type of radioisotope power system that utilizes plutonium-238 and the natural radioactive decay that plutonium-238 undergoes, which creates heat. You then take that heat and through an advanced energy conversion process called the Stirling heat engine, we turn that thermal energy, that heat, into electrical energy or electricity to run all of the instruments on the spacecraft.
And how much electricity are we talking about?
That's the unique aspect about these systems, is that we're only talking about a couple hundred watts of energy, and believe it or not, that's all it takes to adequately power a deep space mission with the ways that we are able to efficiently design these missions and these instruments today.
If that's all the power these instruments require, why can't we supply it with solar? I mean, solar panels on a roof supply an entire building's worth of electricity, including heating or air conditioning.
It turns out that the sun's energy is only sufficient to provide power to a spacecraft at about the orbit of Jupiter. Beyond that, the intensity of the solar radiation is too weak to be able to efficiently turn it into electricity for use on the spacecraft and its instruments. And so the further you go out into the solar system, you need another source of energy for electrical power, and that's where radioisotope power systems come into play.
You're supposed to have 2 flight units ready to fuel by 2017. Are you going to meet that deadline for the ASRG?
Yes, we're on schedule for that.
Okay, but you don't have the 2 flights. So aren't you building, it's like building an engine without a car?
Well, that's an interesting analogy. This is the next generation of radioisotope power system. We have in fact been flying these systems almost since the dawn of the space age 50 years ago. These systems have flown to the farthest reaches of the solar system on Voyager 1 and Voyager 2. And in fact, the Voyager spacecraft have been operating for going on 35 years now. They also flew with the astronauts to the surface of the moon during the Apollo missions. And in fact, radioisotope power system is powering the Mars Curiosity rover that is operating on the surface of Mars literally as we sit here and talk about it right now.
Okay, so there's a long heritage. Why do you need to develop a new one when obviously the old ones worked fine?
Well, the old ones have worked very well and in fact continue to work. But in going forward, by bringing into being the next generation of power conversion technology, we can increase the efficiency of these systems by a factor of 4. And another way of thinking about that is for the same amount of electricity generated, the 200 watts or about 2 light bulbs, we can use a quarter of the plutonium fuel that we would have needed using the older generation thermoelectric conversion technology. And so this is important as we go forward in time to constantly be looking for ways we can improve the efficiency and lower the mass of the systems that we're sending into deep space.
You're working with the Department of Energy on this, and in fact you work at the Department of Energy. What's it like being a NASA guy at DOE?
Well, it's great because it's a chance to take what we do at NASA, blend it with what the Department of Energy does so well, which is nuclear energy and radioisotope systems, and take the strengths of the 2 agencies and work for the good of the nation in developing new power systems for future space missions.
Do you have authority over DOE people? And if so, how do they react to some NASA guy telling them what to do?
I actually serve on a detail assignment at the Department of Energy, so I have the same authority and accountability and responsibility that a Department of Energy person has.
But how do DOE people react to having a NASA boss?
Well, I'm not necessarily their boss. I am a project manager, and so I have both DOE and NASA as well as industry personnel on my project team. And so we are jointly together working towards the advancement and the accomplishment of our goal, which is developing and fueling and testing this new advanced Stirling-based radioisotope power system.
We've got to wrap it up, but I just wanted to give you an opportunity. Is there anything else you think our viewers should know?
I think if there was a takeaway message, it would be to think about this advanced power generation system as a deep space battery that never has to be recharged. It will just continue to develop and generate electricity no matter how long the mission lasts and no matter how dark and deep into the solar system the spacecraft travels.
But this, unlike the other one, has moving parts, a piston that goes back and forth. Is it not more subject to mechanical failure than the previous generation of radioisotope thermoelectric generators?
Well, all of the design and the analysis and the testing that we're doing of this Stirling converter that you refer to is intended to ensure that the system will operate for the long life requirement that we have, 17 years, to allow these very long and deep space missions to occur successfully. So we are confident that we can field that system and accomplish the mission we've been given.
Thank you.
Thank you.